about consensus in Ethereum. Just for context, we're thinking in terms of public as well as private blockchain consensus. No doubt a lot of people are familiar with, high level, probably the public consensus mechanisms, but there are a few there that are being used in enterprise context as well, and I think it's useful just to give you kind of a tour of all the different types and how they're used, so that at least you have kind of a frame of reference there. So I'm going to be touching on failure, which really brings about why we need to have consensus in the first place. Then talking about what distributed consensus is, and then, as I said earlier, just about the different types that we're interested in the context of Ethereum. Okay, so when we talk about failure in Ethereum, there's really a few different levels that we can think of it from. At the very bottom, we've got the failure at in terms of the integrity of the blockchain. So having this would be if the integrity of the blockchain was considered to have failed, then you'd have serious concerns around the underlying cryptographic techniques that were being used in that space. And so one can make an argument there that a lot of the cryptographic techniques, the blockchain technology has been built upon, have been around for a long time. And so even though one could speculate that it is a risk, so much of modern technology relies on these cryptographic techniques outside of blockchain as well, that if this is broken, then there's going to be much wider ranging implications for everyone. You get performance issues as well. So CryptoKitties was a great example of that, whereby we had an application that was released and it really clogged up the network. As more things come along like this, and and more companies develop real technology that uses the blockchain in very good ways, as we saw earlier with Jez's work, it's something that could come around some more. Then of course there's the actual hacks at the smart contract level as well. There's been loads and loads of these over time. There's the DAO was the most famous one, and I guess the first high profile one, but all of the issues, the two multi-sig issues we saw with parity a little while back, and the various exchange breaches and so on and so forth, there's issues there. Then of course there's address zero, which is I think one of the ones that's quite entertaining, in that if you saw on Jez's slides earlier, he was talking about burning tokens, and you burn a token in Ethereum by sending it to address zero. But address zero doesn't just have burned tokens, it also has ether that people have sent there accidentally, because why else would people have sent that much ether to address zero? I don't think people are trying to burn ether as such. So it's kind of like a graveyard of all of this stuff. And you look at the value of all the tokens there. I mean, it is crazy, but no doubt only a proportion of those are there unintentionally. There's a lot there that are intentional as well. Then the other side is consensus attacks too. So the Ethereum network is this big decentralized distributed network, and of course that there's a notion of majority consensus in it. So if you have one node on the network, if you have a majority of nodes that become bad actors, then of course there's concerns around the integrity of it, and kind of all bets are off around what it's actually telling you is the case. So let's talk about the actual distributed consensus side of things. So consensus is at its heart. It's about ensuring that we have some sort of common worldview amongst all of the different nodes within the blockchain. And a key facet of this is what are called quorums. Now, quorums are, you can kind of think of them as being similar to a majority, but they're not strictly speaking a majority. I mean, a quorum from its definition it's ultimately how many votes you need to have within the system to make a decision. Most cases that is a majority, but it doesn't have to be. So, but quorums is kind of a key piece of terminology there. And then you've got this notion of asynchrony as well, in that when you're talking about distributed systems, you talk in terms of synchronous systems, asynchronous systems, and where there's kind of a sweet spot in terms of what's actually practical tends to be this notion of partial asynchrony, because in asynchronous systems, you have to have a notion of time. In order to have a notion of time, you have to have a degree of synchrony within that system. That brings us onto this map here, which is of the Byzantine Empire. Byzantine Empire has been used, it's a reference point that's used a lot in distributed systems, and a lot of people have heard about it from the perspective of Ethereum too. The reason why I wanted to just clarify it is that, especially for those people who aren't familiar with the meaning of the word, which myself included, back when I first got interested in the space, I saw the reference Byzantine again and again, and you think it's something quite fancy, but it's actually very simple what the actual definition is. But it comes back to this notion of the Byzantine generals problem, which is where you have a number of generals that encircle a city. And so these generals, they're all meant to be working together, but they're say you've got a number of them encircling the city, and they need to collectively come to the same decision. So you might have a lead amongst them who can say, right, we want to attack or we want to retreat, but their message needs to get to all the other actors so that they can actually successfully make the right collective decision. And so you have a notion of consensus that's required for that, which is where you have a picture like this. And fundamentally, what it's about is, what's the minimum number of, actors who aren't bad I can have in the system in order to reach a majority consensus. And so this was something that was postulated back in the early 80s in this paper, but it gave rise to this notion of Byzantine fault tolerance. And the key thing here, though, is that, you've got this system where you have four different you've got four different actors in it, and in terms of Byzantine fault tolerance, the minimum number you need in order to make a collective decision of nodes that aren't bad is basically 3, because if you have 2, then it's 50-50. There is no majority there. So the idea is that you can have one bad actor in this, and as long as the other 3 actors are okay, then you're good in terms of the integrity of the system. And so that brings up this notion of Byzantine fault tolerance, but the key thing to remember it as is arbitrary fault tolerance. All it really means is that, if you have an actor in the system that may or may not be bad, but the idea is that they might be sending bad data or something like that, when you talk about something being Byzantine fault tolerance, it's just that it can cope with that scenario. Because a lot of consensus algorithms, they can't. Like, you have ones that have been, that are created, and we'll see examples of this shortly, where you assume that all of the actors in the system are good, so therefore you don't have to plan for this failure. And so that's the key thing there with Byzantine fault tolerance. Okay, so in terms of the consensus in the public Ethereum network, there's, if we start by just having a picture of the network, it's this massively distributed computer. I like these pictures a lot just because it kind of gives you this sense of scale. This isn't the best diagram, but it does show some sort of heat maps for where the majority of the nodes are. I much prefer this one, though, which was from midway through last year, which the lead developer on the Geth Ethereum team tweeted these pictures. He's basically taken locations of where a number of nodes were, fed them into Google Earth, and plotted the results there. And it's just really great representation for all of the different, this notion of it being this big global computer. And the network there, of course, you had Geth parity and then other nodes. So the key there is that most of them were in green. And they represented Geth, but the yellow ones represented parity, and the white was everything else. So in terms of consensus, though, like in public networks, because you've got this notion of bad actors, you have to be quite protective about your interactions with the network. I like to think of it much like in the the X-Files. There was like this ongoing kind of there was like this whole thing of trust no one. They didn't know who they could actually trust out there, who were good actors versus bad actors, and so they always had that sort of in mind with everything that they were doing. And that's what proof of work, the consensus algorithm that's used in Ethereum was and Bitcoin was designed around. So at its heart, you've got the blockchain there, and new blocks get added to the blockchain through all the different actors on the system reaching majority. However, at one point in time, it can be that certain nodes propose a new block in parallel with other entities on the blockchain. And so, what can happen is you get these forks where different blocks start appearing in different places. But the key thing is that you have this notion of the longest blockchain wins. And so with proof of work, the consensus mechanism used in Bitcoin as well as the public Ethereum network right now, it's this idea there. And so I'm not going to go into a lot of detail about proof of work today because I think that hopefully most people are pretty familiar with this. But the whole idea is that you're using this computationally hard problem that all of these miners are competing to solve again and again and again. Again, it comes down to creating this longest blockchain. Yeah, in terms of the actual the usage of the proof of work, that uses a lot of electricity, and this is really the fundamental argument for why we don't want to be using it, because Ethereum right now is between Mozambique and Syria in terms of how much is used collectively by the network. But to bring it on to the more interesting topics, which are these other consensus mechanisms that are available, and so we talk about proof of stake, and this is viewed as the one that's going to help solve these power problems that you have within the Ethereum network currently. And so the idea with proof of stake is that you have this notion of validators on the network. So this is some of the nodes on the network. They're validators. They put up their stake and put it into the network. And then if they validate stuff correctly, they behave as they're meant to behave, then they get rewarded proportionally based on the stake that they put in the first place. But then, of course, if they behave badly, then their stake gets slashed and they lose out. So the idea is it's incentivizing good behavior. I mean, right now with proof of work, the incentive, bad behavior basically means that you're wasting electricity, whereas here you'll actually be losing ether. So there's a fundamental shift there. There's a number of benefits that go with this. So we obviously know that the mining is one significant one. But the other key one is less centralization as well, because if you think about right now with proof of work, where you've got, in effect, the people who've got the most money to spend on hardware, they benefit from economies of scale, because if you can buy lots and lots of GPUs in bulk, then you're going to get a discount for that. If you're building miners on a larger scale than your average person, then of course you're going to be able to get electricity for less. So what that means is that proportionally, the more you spend, the better your return is, versus the people at the other end of the scale who can't afford to pay as much. And with proof of stake, one of the great things is that that's no longer an issue, because your reward is directly proportional to how much you actually put in the first place. So it doesn't matter if you're putting in like tens of thousands of ether as your stake versus less than an ether, you still get proportionally rewarded the same amount. And that's another aspect of why it brings additional fairness to the system. There's another argument for reducing the amount of cryptocurrency that needs to be issued to incentivize people too, because of course right now although there's a lot of speculation built into the price, there's still a view of how much money people need to spend in the first place to actually mine on the networks. And so because there's not this high upfront cost other than actually owning ether in the first place, there's you potentially don't have to actually issue it at quite the same rate that you have done previously. So then within proof of stake, there's a couple of different proof of stake initiatives that you'll hear about. The first one of those is what's called Casper, the friendly finality gadget, which is also known as Vitalik's Casper. So this is, and that's after Vitalik Buterin, obviously, who created Ethereum. And so the idea here, though, is that it's kind of your near-term proof of stake implementation, whereby what's happening in the network is, rather than just trying to do a big bang approach to cut over to it, which obviously is not in anyone's interests, the intention here is that you actually do it incrementally. And so what's been proposed is that every 100 blocks that are mined on the Ethereum network, then they actually get verified using proof of stake. And so this has an interesting property in that it actually brings transaction finality to the Ethereum network. Previously, there's always been this notion of the longest blockchain wins. And so if you have the longest blockchain because you've solved the most blocks, then it could always change due to forking and everything else. But with proof of stake, when you actually have the when you have proof of stake operating every 100 blocks on top of proof of work, what that means is that when the last 100 blocks they get verified using proof of stake, so at that point they're set in stone. So the blockchain can't fork from what happened before that time. So that's where the transaction finality comes in. The other one you'll hear about is Casper the Friendly Ghost, which is also known as Vlad's Casper, and so this is named after Vlad Zamfir, who's one of the lead researchers driving this initiative. And so this is focused on what's called correct by construction, which really is it's meant to be a rigorous proof of stake implementation. And when we say rigorous, we mean academically rigorous, so it can be formally proven and so on. But the idea is that rather you start off with figuring out what the properties are that you want to achieve, and then you actually derive the protocol from that. So it's more of an incremental sort of approach in order to do it. And so this is kind of your research piece that's a year or two, maybe longer, maybe a bit less, who knows, down the line, but it's likely to very heavily influence the proof of stake implementation when Ethereum cuts over to it in anger. In terms of when it's going to happen, initially people were talking about last year, and then I think really people started to realize how hard a challenge this is. But for Vitalik's Casper anyway, the one that does the transactions finality every 100 blocks, that's an alpha network went live at the beginning of this year, and so at least progress is being made there in a real environment. Okay, so that's public blockchain consensus. Talking about private, and so this is really what's happening in the enterprise Ethereum space. So we have I'm sure most people anyway are aware of Quorum, which is one enterprise Ethereum client. There's a number of other ones that are being worked on, and like Clearmatics has got one here, who are one of our sponsors, but there's also Block Apps and Consensus are working on one too, and it's a space that this year and next you're likely to see a lot more movement in, especially with the work within the Enterprise Ethereum Alliance. We're actively focused on standards, and there being code to support these standards as well, which you'll be hearing about more soon. But in terms of the actual consensus algorithm, so you've got one which is called proof of authority, which isn't one that's specific to Quorum. It's something that came out of Parity and Geth, the public Ethereum technologies. But it's something that was kind of created with a view for private Ethereum networks. And so the idea here is that it uses majority consensus, and you just have a set of nodes in the network that can create blocks. So you basically take a certain number of nodes and you say, right, these are your validators, and they propose blocks which contain all the transactions that have happened since the last block, and then if the other nodes are okay with it, then they just say, yeah, thumbs up, fine, we'll get that gets added to the blockchain, and then they keep going. So it's a fairly rudimentary consensus algorithm that works in private blockchain deployments if you have a sort of fairly sticky set of nodes there, but it's also used in the public Ethereum test networks as well. So both Coven and Rinkeby, which are the kind of the reliable test networks, are using this kind of consensus mechanism. So you've got a number of companies or people who are running up some validator nodes, and what it means is that you have a more stable blockchain environment for testing on. One of the other types of consensus is known as Raft, and so Raft was something that's been used. It's gathered a lot of momentum in the last sort of 10 years in the distributed system space. So things like Kubernetes and all these big sort of orchestration tools that are being used a lot in just general tech, they make use of this consensus algorithm. And so the idea here in Raft is you've got what's called dynamic leader election. So all nodes in effect start equal within the network, and then what happens is that a node puts its hand up to say, I propose that I'm a leader. Other nodes then vote to say, yeah, we're prepared to support that. Then that node becomes a leader, and then it just starts authoring the blocks. And so the key thing, though, to keep in mind there is that what I was talking about earlier, that you have, using Raft consensus anyway, it's something that you want to use in a sort of private environment where you kind of control the different nodes. So talking about these different states that a node can be in, we've mentioned this notion of an elected leader. So at any point in time, a node can be, a candidate, which means it's put its hand up to be, become a leader, and then one becomes a leader, and then all of the other nodes are followers. And so what that looks like is that you have here you've got S2, which is your leader node, and so it broadcasts out these heartbeat messages to all the other nodes, and then when messages come through, it replicates those messages to the actual other leaders there. So the key thing just to remember is that it receives these messages and broadcasts them out and gets messages back, and so that's what this is showing. The actual process itself, though, if we talk about with a specific transaction with it, so when we're talking about consensus on a blockchain, what it means is that the leader who's been voted within the network to be the node that's been had the votes to become the leader, is aggregating all the different transactions that don't currently reside on the blockchain. Then it basically puts together a block in the same way that a miner right now proposes a new block, and then it replicates that block to all of the other followers on the network. And then what it waits for is those nodes that it sort of broadcasts out to all of them to come back and say, yeah, we've written that to our log, and they send a message back. And then when that leader has a majority of the nodes actually saying that they've received a response back, then it commits the block itself. And then after that, it actually sends out another message out to the nodes to say that this block is being committed. So that's how the consensus work. But there is clearly, significant problems there in that it doesn't provide Byzantine fault tolerance. And so, if you think you've got this notion of leader election, and so you could have arbitrary nodes just, kicking off new leader elections midway through, the regular processing of blocks, and it's just quite easy to sort of wreak havoc on the actual network, and that's why it's not considered, resilient anyway in sort of networks where there could potentially be some bad actors. And so those are just some of the things that can actually happen there. So that then leads on to what's called practical Byzantine fault tolerance. And so this is something that was proposed in a paper at the end of 1999. And then the idea is that you've got your different nodes on the network, and then a subset of those nodes are validators, and there's a multi-phase commit process that happens. So when we say multi-phase, much like you saw with Raft, like a block gets proposed, and then other then other followers actually committed and notify the leader. With practical BFT, it's a similar thing that happens, but there's a lot more communication between the nodes, so that has the properties to make it Byzantine fault tolerant. And so these three phases, it's what's called pre-prepare, prepare, and commit, which I'll show you in a minute. But the idea is that, again, if you think back to our picture of the Byzantine generals problem, where you have, if you've got 4 nodes in the network, you can have one of those nodes being bad and the other 3 are all good still. And so a company called AMI in Taiwan, they actually implemented PBFT in what they've called Istanbul BFT, which is really just an implementation of this consensus algorithm. And so the idea is that you've got these nodes, and there's always going to be one node that initially proposes the next sort of block to add to the blockchain. And this is done in a round-robin manner. So you think about your network of nodes, and then this one's the validator. Then subsequently you just work your way around. And so what happens is that validator node, once selected, it then sends out what's called a pre-prepare message, which is just to sort of tell the other nodes on the network that this is what we're thinking as the next block to add to the blockchain. And then all of the validators have to broadcast the prepare message, which is basically taking that prepare message and sending it to all of them. So what it means is that every node kind of sends everything to every other node. And so it really kind of fans out, which I'll show you in a moment what that looks like. But then each the key thing here is that because these messages are kind of fanned out between all of the different nodes independently by one another, each of them independently verify that that transaction is valid to be added, that block is valid to be added to their view on the blockchain. And so when you actually see these flow of messages happening and each of the individual nodes independently see see the right number of messages having been sent to them, they're able to actually commit the message. And so that's where you actually get your consensus. So it's a lot easier to see in terms of a picture here. So you have your validator that proposes the initial block, and then it sends out this pre-prepare message to, your proposer, and sends out this message to all the other validators in the network. Then all of the other validators send out this prepare message to one another, and so each of them independently at this point is confirming that they've actually seen that, that they've seen a majority of nodes send that prepare message. And as long as they all each independently see a majority of nodes would send that same message, then you get your commit, and that's the point where it's added to the blockchain. Yeah.
So the validation of the blocks is done before the pre-prepare, and then the prepare is sent. The commit is sent once a majority or enough people. You've seen the prepare from enough people.
Yeah, exactly. So the propose is basically your new block for the blockchain, and then they all just independently, validate, verify, and then validate that they're happy with it.
Before sending the prepare message.
Yeah, as in they'll validate it, and then this is more just for reaching consensus because you have those multi-phases there.
Are there multiple proposes, and then the quickest one wins to get to the commit state?
It's not. No, I mean, each of these levels you need to have a majority. So for once you get to this, the pre-prepares all being sent out. So if one node's faster than all the others, it's not going to matter because you need to have a majority that are fast. You'd have to have a majority that are faster than all the others for it to work. Okay.
How's the proposer chosen?
So that's done in a round robin manner within the network. And that was actually all I was going to say about the consensus stuff. So at least, I hope from this you've got, a good idea about now. I'm sure you'd heard of proof of work before and, had some familiarity with it. But now when you hear people talking about proof of stake, you actually know, where it all is and can understand some of the differences between the different consensus mechanisms used in private networks as well. Cool. That's all I had to say. Thank you. Some questions. Actually, could I? It's being recorded. I thought we should actually use the microphone. I've just realised. Yeah, thanks, Oleg.
Hi, Conor. Scott Riley. Thank you. That's a brilliant layman's introduction to consensus. Just going back to Ethereum and the proof of work and what's your feeling about, because they talk about ASICs now being available for Ethereum network. So what implication do you think that will have, and how long before that sort of dissipates through the system?
So I haven't actually looked to see, what the ASICs that people have started saying could be capable for Ethereum are able to do. I know that historically, because in the mining used in Ethereum, it uses this thing called the directed acyclic graph, which basically means that each time someone generates a value that could be a potential solution to create a new block on the blockchain, they then have to do a lookup in a large area of memory that's associated with the actual GPU. So I don't know if extending the actual size of the DAG could be a way around that or not. I'd need to have a look. But historically anyway, that's what has happened in Ethereum in order to prevent ASICs, which are basically these integrated circuits which are really good at doing one thing but not much else from being used.
Thank you for your talk. I just wanted to clarify on your proof of stake slide that you said that proof of stake leads to less centralization.
Yeah.
What do you think of arguments that proof of stake actually leads to more centralization because of a few people have coins and then they get their rewards and then they have more coins and then it leads to a few parties controlling the network, and also on the point of stake grinding and how that can also lead to centralization?
Yeah, so, sorry, with what was the second one you said?
Stake grinding. So stake grinding is basically where the people who have been selected to receive the reward can basically change like the hash function so that they can kind of pick the next people that select to receive the reward, and then that can also lead to like centralization as something maybe to look into.
Stake grinding, I'm not so familiar with the details of, but yeah, I mean, there's certainly it's a valid argument that there could be more centralization if people have very significant amounts of the cryptocurrency. And there's, I think it kind of comes back to this idea as well, just generally with cryptocurrencies, it's harder to launch one in the first place with proof of stake unless you have fairly well distributed in the first instance. Yeah, so it's, I don't, myself, I don't see that there's, an obvious way around it, but yeah, there is potentially, that is a valid argument there. But I guess it works both ways because, of course, with right now, power being the thing that people can dominate with, provides its own centralization. And there was actually a recent talk that was done by the team at Cornell and IC3 where they actually analysed how decentralized the Ethereum and the Bitcoin networks are, and so that's a really good piece of academic research if you want to actually see really how decentralized these networks are, because there's you're talking, although there aren't any entities with over 50% on the networks in the Ethereum network, there are entities that could already control about sort of 25-30% of it. So there's much as we all love the decentralized technology, there isn't actually as much decentralization there as one would think.
Robert Olson from Radix DLT. Really enjoyed the talk, second time in 2 days. What's your favourite solution between Vlad and Vitalik's Casper ghosts?
Well, I think being quite pragmatic, I think that where Vitalik's coming at it from the perspective what we can actually do nearer term, whereas Vlad's sort of that much further down the line. So I'm keener on what Vitalik's proposing nearer term, and with Vlad's approach, it's not something that I've spent a lot of time looking at in detail to get my head around all the intricacies of it. So I wouldn't have a strong opinion on it at this point.
One question from me actually. The consensus protocol mechanism you called Raft, is that basically like a delegated proof of stake, like Neo, for example, is using it, or is that a different animal altogether?
It is delegated in terms of you have someone who's who's the leader, but the thing with Raft is it can just constantly, it can change on a whim, and there's not anything in the network to kind of prevent it rapidly changing. It's more that you just assume all of the actors are good there, and there aren't any bad actors.
I had a question about the EA and perceived levels of trust in private networks. Obviously, the more trust you can assume, you can trade off against performance and throughput. Is there any consensus at that level, or is it just kind of it depends?
I think within the EA right now, the view is that there is a need for Byzantine fault tolerance, and mainly because if you think about all being well and these member networks growing larger and larger, there can come a point where you could have a very large, say just a large financial institution, then you could have a small startup on the same network, and those large financial institutions, they're going to need to be sure that these smaller players who they won't necessarily know or want to really know too much about who they are, that they can't disrupt the network. And so, although I think early on there was some thinking that something like Raft could be applicable, I think that the reality is that because of the different sizes of the entities who could all be playing in the same playing field with blockchain, you need to have a degree of just BFT really built into it.
I suppose you have to accept that large validator sets you get much slower settlement times than BFT.
Yeah, and the other thing with BFT solutions is that they're sure. I mean, in the public networks, you obviously pay a big. You have to pay. You've got to pay significant premium in terms of just the. So you've got to trade off a significant amount of transaction throughput in order to be able to store something that can kind of arbitrarily scale to not an infinite number, but a very large number of nodes. And I think in order to actually have that sweet spot between able to actually process the right number, process the sort of transaction rates that enterprises need, there'll probably come a point where you don't use, well, I'd say you wouldn't be using a consensus mechanism where anyone can potentially contribute to the overall consensus of the system, because once you've got to sort of hundreds of nodes, for instance, then these algorithms are just going to get harder and harder, and they're going to start to get more and more expensive to run. So you probably find that there'll be a kind of top in terms of, right, we have this level of trusted nodes because they're large enterprises or whatever else who we think they know what they're doing anyway. So yeah, it's that's kind of where the trade-off's at right now.
So my question is even more kind of broad level. In the choice between going on a proof of stake versus having a Lightning Network kind of a solution, which does some off-chain transactions while maintaining the sanctity of proof of work. I mean, what are the drawbacks and the pros and cons of doing both of them?
I think it all comes down to the requirements that you have for it. And so to reference like Jez's talk earlier on, like it was really impressive to see what they were doing with state channels technology, but then you still had to have that notion of settlement there. So if you if you're an institution that needs every single transaction to be set in stone, you can't afford for them to periodically just be kind of brought back on chain. You have fundamentally different use cases for the technology, and so you just don't have that one size fits all. I think his example was really good for how you can use state channels to achieve a much greater throughput, but you still have to bring the stuff back on chain at some point. And it really depends on how comfortable you or the business or whoever it is are with having that notion, working around failure scenarios in those sorts of situations.
But those offline chains still kind of follow the protocols of the main chain, don't they?
Yeah, they do.
So,
but
so any problems on those off chains will probably be validated on the main chain anyway, isn't it?
So it depends on whether it's. I mean, when I talk about problems, I'm thinking in terms of failure scenarios and these sorts of things. So it's ensuring that you have, if you want guarantees of something that something's happened and that it has to happen on the actual chain, or you need to have the infrastructure into place to provide guarantees that you'll be able to get it back on the chain through some sort of recovery semantic. But it comes down to really what the specific use case is there. Because there's always going to be trade-offs with it. You're never going to have one that ticks all the boxes. It's just about what you need for your specific problem. Okay, all right. And so with moving on just about the meetup. Okay, thank you.